You spend thousands of dollars on a high-end workstation. You load it with maximum memory capacity. You open a massive architectural render or launch a heavy simulation, and the computational load immediately shifts to a very specific piece of hardware: RAM, random access memory. It is the digital concrete of our era. Every polygon in a complex 3D model, every single frame in a competitive shooter, must pass through these physical pathways. It is the critical speed buffer between long-term storage and your processor. Without it, the world's most advanced technology simply cannot function. We tend to think of consumer electronics as a limitless, hyper-competitive free market. But if you look at the physical supply chain, a very different reality emerges. Decades ago, the memory market was crowded with dozens of manufacturers. But creating these microscopic components is one of the most difficult engineering feats in human history. Building a single modern semiconductor fabrication plant costs upwards of $15 billion. The barrier to entry is astronomically high. Driven by these extreme costs and decades of market consolidation, the global landscape shifted. Today, the vast majority of the world's DRAM supply is produced by just 3 major corporations. This isn't a secret. It is a textbook economic oligopoly, born from the sheer physical difficulty of manufacturing. This highly concentrated market is historically prone to extreme friction. The semiconductor industry operates on brutal boom and bust cycles. Periods of oversupply lead to crashing prices, while sudden demand triggers massive shortages. And in highly concentrated markets, these cycles require strict regulatory oversight. In the early 2000s, during a different technological era, several major memory manufacturers faced investigations and significant punitive price-fixing practices. While the market is heavily regulated today, the underlying economic reality remains. When 3 entities control such a significant share of the physical foundation of the digital economy, the global market becomes highly sensitive to their production decisions. This highly concentrated market was functioning smoothly until a new, unprecedented demand entered the system: artificial intelligence. The trillion-dollar AI sector doesn't just run on complex algorithms. It requires a massive physical infrastructure, specifically HBM, or high bandwidth memory. To understand why AI caused such a disruption, you have to look at the physical architecture of the hardware. Standard RAM is two-dimensional. It is a single-story building. Data travels across the motherboard to reach the processor, much like traffic on a standard 2-lane highway. But artificial intelligence, particularly the processors designed by companies like Nvidia, processes massive, complex data sets simultaneously. A 2-lane highway creates a catastrophic bottleneck. The engineering solution was HBM high bandwidth memory. Instead of laying memory chips flat, hardware architects stacked them vertically, like a microscopic skyscraper. They connected these floors using thousands of microscopic vertical pathways called through-silicon vias TSVs. This 3D architecture allows the GPU to access massive amounts of data at extremely high bandwidth and with significantly reduced latency. However, building these microscopic skyscrapers requires extreme precision and complex packaging, drastically reducing the overall volume a factory can output. If standard RAM is a small suburban house, HBM is a 100-story skyscraper. It requires significantly more manufacturing complexity and production capacity. But you cannot simply build a $15 billion factory overnight. Faced with a sudden surge in demand from the AI industry, manufacturers made a logical business decision. They reallocated part of their production capacity toward higher-margin HBM products. That decision reduced the amount of manufacturing capacity available for conventional memory, contributing to tighter supply and higher prices across the broader technology market. The media quickly framed this shift as a global chip shortage, and while supply chain disruptions certainly played a role, the underlying economics were more complex. Extreme demand colliding with limited manufacturing capacity created powerful market incentives. In macroeconomics, high prices often encourage structural adaptation. As the cost of standard memory increased, the broader technology industry didn't simply absorb the pressure, it began to adapt. A supply bottleneck often becomes an invitation for innovation. Think about a complex exterior facade project. If the cost of standard aluminum composite panels quadruples overnight, you don't cancel the building. You redesign the envelope. You use parametric modeling to optimize the geometry, drastically reducing material waste. while maintaining structural integrity. The technology sector has followed a similar path. Years of inexpensive memory reduced the commercial pressure to aggressively optimize software in many applications. But as memory became more expensive, efficiency once again became a competitive advantage. Developers revisited rendering pipelines, memory management, and engine optimization. In many areas, software became leaner, faster, and significantly more efficient. Simultaneously, hardware architects began redesigning the very foundation of computing. They moved toward tighter integration between processors and memory in certain system designs. Instead of treating memory as an increasingly distant component, some manufacturers engineered unified memory architectures that placed memory physically closer to the processor. It is the equivalent of prefabricating an entire complex facade unit inside a controlled factory environment, reducing assembly complexity and improving efficiency. These architectural changes reduce latency, improve bandwidth, and simplify data movement. The changing economics of the memory market didn't stop technological progress. If anything, these market pressures accelerated the search for alternative architectures, custom silicon, advanced packaging technologies, and new semiconductor manufacturing capacity. If you look at the broader picture, this goes far beyond ordinary manufacturing decisions. It reflects a fundamental geopolitical transition. We are entering a world where high-performance silicon is becoming one of the most strategically important industrial resources on Earth. During the 20th century, industrial power depended on physical energy infrastructure. Today, an increasing share of economic power depends on computational infrastructure. The critical pathways are no longer pipelines. They are microscopic circuits. This structural bottleneck is further complicated by physical geography. The modern computational supply chain is deeply concentrated in one of the most geopolitically sensitive regions on Earth. The advanced AI processors are predominantly fabricated in Taiwan. The complex high-bandwidth memories manufactured largely in South Korea, and the intricate 3D packaging that binds them together happens along the exact same narrow supply routes. This creates a highly fragile geographical triangle: a single seismic event, a regional power grid failure, or rising geopolitical tensions in East Asia doesn't just delay consumer shipments. It represents a potential disruption to the computational infrastructure of the global economy. You might believe these manufacturing decisions don't affect you because you don't operate AI data centers. But memory has quietly become an embedded cost throughout modern life. Every modern vehicle, from a basic utility truck to a luxury electric model, relies on dozens or even hundreds of memory chips to manage safety systems, infotainment, sensors, and core operational software. When supply becomes constrained and component costs increase, manufacturers face higher production expenses. Those costs are often passed through the supply chain and eventually reach consumers. You walk into a technology store and see 50 different laptop brands. It feels like unlimited competition. But beneath the plastic chassis and the marketing logos, many of those systems ultimately depend on the same small group of global memory manufacturers. Consumer choice is broad. The physical supply chain behind that choice is far more concentrated. At the same time, modern software continues to demand more computational resources. High-resolution assets, real-time ray tracing, AI-assisted features, increasingly complex simulations, and larger data sets all require substantially more memory than they did only a few years ago. As a result, hardware replacement cycles continue to accelerate. The combination of rising software demands and a highly concentrated manufacturing base makes the digital ecosystem remarkably sensitive to disruptions. Even temporary production interruptions at major fabrication facilities can ripple through global technology, supply chains, and influence pricing over time. That is how interconnected the architecture of our digital civilization has become. The AI revolution isn't simply another technological milestone. It represents a profound reallocation of industrial investment toward computational infrastructure. Capital, talent, manufacturing capacity, and national strategy are increasingly converging around advanced silicon. The digital landscape is evolving around this new center of gravity. The next time you open your architectural rendering software or launch a large simulation, and your system struggles to load the environment, remember, your computer isn't simply slow. It is operating inside a physical ecosystem shaped by manufacturing constraints, economic incentives, and one of the most concentrated supply chains in the modern world. The architecture of computing is becoming faster, leaner, and more capable, but also increasingly dependent on a remarkably small number of critical manufacturers. New production capacity and alternative technologies are being built, yet for now, access to high-performance memory remains one of the defining bottlenecks of the digital age. This is Project Sway. We dissect the mechanics, subscribe, and stay analytical. Until the next case study.